Hi, in this video we are going to continue on the organic chemistry, and in this part we will be talking about aldehydes and ketones, and later on we will talk about the carboxylic acids. Okay? Now, for aldehyde and ketone, first of all, I understand that for most of you may not be that familiar with these two homologous series. So I will talk more about their basic information, and then we will move on to the chemical reactions. Now, here we have alkanals and alkanones, right? So these are the most traditional way of naming the homologous series, but in DSC we will usually go for aldehydes and ketones, okay? Now, you notice they are very similar because they both have this CO double bond, right? So this CO double bond, we will call this the carbonyl group, okay? This is also the functional group of aldehyde and ketone. So you see both aldehyde and ketone contains carbonyl group, okay? Now, you notice the difference is that for aldehyde, it has a hydrogen connected to the carbonyl carbon. Now, sometimes we try to describe different types of carbon. This one, we can describe it as the carbonyl carbon. Basically, the carbon involved in the carbonyl group, we can call this the carbonyl carbon. Okay, so you see for aldehyde there is a hydrogen atom attached to the carbonyl carbon. Okay, for ketone, on the other hand, it has an al group attached to the carbon. Okay, so this al group actually representing an AQ group. So it could be a methyl group, ethyl group, something like that. Okay. Now, so you realize that this is the key difference, and what's more is that for aldehyde, this R, which again is corresponding to the AQ groups, it can also be hydrogen atom. So in fact, the first member of aldehyde is actually having the carbonyl carbon connected to two hydrogen atoms. That one will be the methanol, okay? So that's the idea. However, for ketone, the R must be corresponding to the AQ groups. Therefore, the first member of ketone is actually already 3 carbon, which is propanol. Okay, propanol. Let's put it down. Okay, if we talk about the first member for aldehyde, okay, it is methanol. Okay, with 1 carbon only. But for the first member of ketone, it is already having 3 carbons. Okay, so bear in mind. Now, let's look at the functional group. Like I said, both of them will have the carbonyl group. Sometimes we can also describe the functional group as the aldehyde group and the ketone group. Okay, bear in mind, if the question asks you what is the functional group of a compound like this, then you must put down either carbonyl group or aldehyde group. Bear in mind, you cannot simply say aldehyde. Oh, it has an aldehyde. Because aldehyde is also the name of the homologous series. So if you want to use aldehyde, this word to represent the functional group, make sure you add the word group at the end. Okay, that would be much more clear. Okay, there are some general remarks. Now, if you look at these two compounds, because of the very electronegative oxygen atom, these two are polar. However, you notice there are no hydrogen atom attached onto the oxygen atom. Therefore, between the molecules, they cannot form hydrogen bond. They can only have van der Waals force. Okay? So their physical property, if you see here, methanol and ethanol, they are colorless gas. And starting from propanol, it will be a colorless liquid. Okay, so you notice is boiling point is actually lower than alcohol, because alcohol with the hydroxyl group, it can form hydrogen bond, but here it cannot. So therefore, it has to, only with 3 carbons can it exist as a liquid in room temperature and pressure. Okay. For ketone, most of them are colorless liquid, because remember, even the first member is already having 3 carbons. Okay. Now, for aldehyde and ketone, they have a sweet and pungent smell. So, in other words, they have a strong smell. For girls, probably you do nail varnish, right? You basically, right, color your nails, right? Beautiful colors on the nails, right? And after that, you need to remove the nails, right? There is a particular solution or a liquid that allows you to remove the nail varnish, and that one is called the nail varnish remover, and that one is actually ketone. And for those of you who have that nail varnish remover, once you open it, you get that very, I'm not sure whether you get it, but it's like fruity or sweet smell, probably not that pleasant, but in chemistry we would call that a sweet or fruity smell. Okay, that would be ketone. Aldehyde actually it varies. Some aldehydes are pleasant, some aldehydes are not. Like all of you should have at least smelled coffee, right? And actually coffee, with that so distinctive pleasant smell, a lot of the reason why they have such a smell is due to the aldehyde involved in the coffee. Okay, so at least you get an idea that aldehyde and ketone are having strong smell. Okay, strong smell. All right, and you see a lot of perfume, aromas, fragrance. They actually have a lot of aldehyde and ketone inside. Okay. All right, so let's talk about more on the physical property. Again, it all boils down to the intermolecular force, and like I said, it has the carbonyl group, makes it polar, and therefore having relatively strong van der Waals force, but not as strong as those with hydrogen bond. So you see here, aldehyde and ketone, they have higher boiling point than alkane, alkenes, but lower boiling point than alcohol, amine, and carboxylic acid, because these 3 guys, they can form intermolecular hydrogen bond. So kind of in between. Okay, and we say that low carbon aldehyde and ketone, so we are talking about like with 1 carbon, 2 carbon, 3 carbon, something like that. They are soluble or miscible with water because they can form hydrogen bond with water molecule. So bear in mind, even though it cannot form hydrogen bond between its own molecule, it is possible to form hydrogen bond with water molecule. So it makes it slightly soluble in water. Okay. Okay, and like I said, aldehyde and ketone, they are relatively volatile because, of course, think about it. If you get strong smell of the compound, it means that there is a lot of gaseous molecule of that compound that is able to enter your nose, and then you get the smell, right? So basically, when you have something that has a strong smell, that liquid is very likely to be very volatile. Otherwise, you can't get that gaseous molecule entering your nose, right? So liquid aldehyde and ketone are relatively volatile, okay? Now, so these are some basic information about aldehyde and ketone. Now let's step into the chemical reactions. There are not many chemical reactions. There are 2, which is oxidation and reduction, okay? So for oxidation, actually we did talk about that already. Remember when we talk about the alcohol, okay, let's go back to our previous page. Over here, do you remember for alcohol, for the oxidation of alcohol, it depends on the type of alcohol, whether it is primary alcohol, secondary alcohol, or tertiary alcohol. they can oxidize to different extents, forming different products. Okay. Now, if you remember, for primary alcohol, it can undergo an oxidation to form aldehyde, and the aldehyde is able to undergo further oxidation to form carboxylic acid. So in this case, actually, it is not the oxidation of alcohol, it is the oxidation of aldehyde to form carboxylic acid, right? So here, that makes it one chemical reaction for aldehyde, okay? So we did talk about that. So over here, we will say that aldehyde can be oxidized to carboxylic acid easily by oxidizing agent, such as acidified potassium dichromic solution. And actually, if your aldehyde is exposed to air long enough, even the atmospheric oxygen is able to oxidize the aldehyde to carboxylic acid to a certain extent. Okay? So here you see, this is ethanol. Now we recognize this aldehyde functional group, right? It oxidized to form ethanoic acid. Again, when you look at the oxidation or reduction, you do not necessarily need to look for the oxidation number. In this case, it is quite obvious that during this reaction, the compound gains an extra oxygen atom. So this one has to be an oxidation of organic compound. Okay? However, for ketone, you realize that it is resistant to oxidation. The reason is because, think about it, if you want to become carboxylic acid, you need to have OH. If you put an OH here, then the carbon will have 5 bonds. It doesn't make sense. And you may ask, hey, can I take away the methyl group? The answer is no, because carbon-carbon bond, you may realize, we rarely split a carbon-carbon single bond. Okay? We may open up a carbon-carbon double bond, but a carbon-carbon single bond, we rarely split it. Okay? The only situation where we split a CC single bond is when we are doing cracking. Okay, cracking. But you know, in cracking, we are talking about 500 degrees Celsius and with a catalyst. Okay, so under such an extreme condition, the CC single bond actually breaks. Okay, so that's one of the reasons why it is resistant to oxidation. Okay, so you realize that aldehyde does undergo oxidation, but ketone does not. So that makes this particular reaction a very good reaction to distinguish between aldehyde and ketone. So you see here, down here, we say that acidified potassium dichromic solution is commonly used to distinguish. Right? I'm running out of ink. Let me change another blue ball pen. There you go. Okay, it's commonly used to distinguish between aldehyde and a ketone. So only aldehyde will reduce the orange dichromic ion into green chromium 3 ions. Okay, so bear in mind this one was frequently asked. Okay, to distinguish between aldehyde and ketone. Okay, bear in mind. Now, another reaction is reduction. Okay, we have oxidation, we have reduction as well. So, as you can tell, for oxidation, let me add a remarks here. For oxidation, you know the organic compound will have more oxygen or less hydrogen, right? We say that for oxidation, it will have an increased number of oxygen atom and or decreased number of hydrogen atom, right? So for reduction, that will be another way round. For reduction, we can determine whether a reactant is reduced or not by looking at whether there is a decrease in oxygen atom or whether there is an increase in hydrogen atom. Okay? Now, we say that aldehyde and ketone can both be reduced to alcohol. So you see here, this is an aldehyde. When it undergoes reduction, again, I want you to focus on the functional group, okay, or the carbonyl carbon, and what does it become after the reaction? You see, after the reaction, it has gained 2 hydrogen atom, which fulfills this criteria, and therefore this reaction is a reduction reaction. Okay. Similarly, for ketone, this is the carbonyl carbon, and after the reaction, you see, boom. Obviously, it has gained 2 hydrogen atoms as well. Okay, so this is what we say reduction. Okay, gain hydrogen atoms. Now, for the reduction, it depends on whether you are aldehyde or ketone. If you are an aldehyde, you will be reduced into a primary alcohol. Right? If you are a ketone, then you will be reduced to a secondary alcohol. Right? That makes a lot of sense because if you go back to the oxidation of alcohol, we say that primary alcohol is oxidized to aldehyde, whereas secondary alcohol is oxidized to ketone. Now we are just doing the other way around, just going back to the original alcohol. So that's why that would be the corresponding product. So would there be any reduction that results in a tertiary alcohol? Of course not, because at the first place, tertiary alcohol is resistant to oxidation. So how can anything resistant to oxidation generate an oxidized product that can be reduced back to its own? Okay, it doesn't make sense. So that's why there is. Now, you may also see, sir, why is it like 2 different conditions? In fact, for the reduction of aldehyde and ketone, we have 2 common reducing agents that can accomplish the task. And it doesn't matter which one. Okay? Let's have a look at this reducing agent that is exclusively used to reduce organic compounds. Now, these are something new to you. Okay? We have lithium aluminum hydride, LiAlH4, and then sodium boron hydride. Okay, NaBH4. Now, you notice they have similar structure. The only difference is the cation and the central atom of this molecular ions, okay? Of these ions, basically. Now, the structure itself is quite interesting and quite rare as well, because now you see on the whole, this is an ionic compound, right? Ionic compound, positive, negative. And if you look at the negative ion, it is a polyatomic ion where we have a metal. Forming covalent bond with a non-metal hydrogen, right? So it's quite rare to see a metal forming covalent bond with a non-metal, right? Because metal usually form ionic bond or maybe metallic bond, okay, with itself, okay? So it is quite rare to see something like this. Now boron, despite of being a semi-metal, again, we rarely see semi-metal forming covalent bond. What we did because silicon also forms a covalent bond with oxygen atom, right? So anyway, this is how the ion looks like. You may not necessarily need to recall the structure, but well, at least you know the formula. Okay. Now, we say that both reducing agent, how does they reduce the aldehyde and the ketone? Now, I just mentioned that if you focus on the carbon bearing the functional group, when they undergo reduction, they gain extra hydrogen atoms, right? When they undergo reduction, they gain extra hydrogen atoms. So if you are a reducing agent, if you help others to undergo reduction, you may as well provide hydrogen atom to the species that is undergoing reduction, right? So actually these 2 reducing agents, they help others to undergo reduction by providing hydrogen. So you see, they provide hydrogen, but in the form of something, again, special. We call it hydride ion, H-. Okay? H-. Usually when we talk about hydrogen ion, we're talking about H+, right? H+. Actually, if you think about it closely, hydride ion is also considered stable when it comes to the doublet rule, right? Doublet rule. So hydrogen originally has one electron only, and for H+, you just lose that electron, so you have no more electron, and we can consider that one stable, right? But on the other hand, if you get an extra electron forming H minus, it actually have the same electronic arrangement as helium, which according to the doublet rule is stable. Okay, so hydrogen ion is actually okay to exist, but to be honest, it's not very stable because with one proton holding two electrons is quite demanding for that one proton. Okay. Now, anyway, for this hydrogen ion, they will be added to the carbonyl group of aldehyde and ketone in order to reduce them into alcohol. Okay. Now, for the detailed reaction mechanism, you don't have to know. Okay. But these are something that you need to pay attention to. Now, you may ask, if these two work very similarly, what is the difference between the two? Well, it turns out that this guy, lithium aluminum hydride, is a much more powerful reducing agent, much stronger than the sodium boron hydride. So it's a very powerful reducing agent, and it's so powerful that it can react violently with water. Okay? When something that is powerful, that means it is very reactive. So lithium aluminum hydride, just like group 1 metal, they must be stored under paraffin oil. Okay? And when you use it, you can't just take it away from the paraffin oil because we have moisture in the air. So it must be used by first dissolving into dry ether solvent. This is important. Okay? It must be used by dissolving it into dry ether solvent. Okay? Then we also look at a little bit about the reduction process. So first of all, if you use lithium aluminum hydride, we will first perform the reduction using the lithium aluminum hydride. Now, after the reduction has complete, we need to do another step. Okay, and this step is important because we try to remove any unreacted lithium aluminum hydride. We don't want any unreacted lithium aluminum hydride to stay there, or otherwise it may react with moisture in the atmosphere and therefore having some unexpected reaction that could be jeopardizing. So that's why we need to remove the unreacted lithium aluminum hydride by adding dilute acids. And one of the usual choices, of course, HCl or H2SO4. And this is to remove excess aluminum hydride. Okay? So always remember, when we use lithium aluminum hydride, we must do it in a two-step manner. One, we actually carry out the reduction, make sure the lithium aluminum hydride is dissolved in dry ether. And the second step, what we did is we add dilute acid to remove any unreacted lithium aluminum hydride. Okay? Now, a brief remarks here. You see how we describe the reagent here. Now, if you see something like this, lithium aluminum hydride / dry ether, it doesn't mean that it doesn't mean that, we can use lithium aluminum hydride or dry ether. No. This one means that the lithium aluminum hydride is dissolved in the dry ether. Okay? This is how we represent the ideas. So this / doesn't mean or. It means dissolved in or used together with. Okay? So that's the idea. And after the reaction is completed, then we should have the alcohol, and then we can separate it from the mixture by a fractional distillation. Okay? Now, what about sodium boron hydride? Okay? So, like I said, lithium aluminum hydride is so reactive, so dangerous. To be honest, we don't have it in our school lab. We are not allowed to because it's so reactive. Sodium boron hydride may be able to store in the school lab because it is a less powerful reducing agent. Okay, it's a less powerful reducing agent, and they are often used as a safer alternative of lithium aluminum hydride. Okay, it's a less powerful one, and it can do the job. So why not? And because it is less powerful, it is less dangerous, and they can be used in aqueous solvents. So that means water. It can be used in water. And also, it does not require a second step. It doesn't really matter if there is unreacted sodium boron hydride, because it's not very dangerous. Okay? So that's the idea. Down here is just something extra. Actually, the reaction, like I said, no matter it's lithium aluminum hydride or sodium boron hydride, they undergo reduction. They help the alcohol. They provide the hydride ion to reduce the aldehyde or ketone, right? So actually, the reduction reaction does not generate the alcohol straight away. Instead, they will generate something called alkoxide. Alkoxide basically is an alcohol with an H plus taking away. Then we have an alkoxide ion. And alkoxide is highly unstable, actually highly basic. So we need to add the acid where H plus is provided, and we try to add the H plus back to the alkoxide, forming the alcohol. Okay, and the addition of acid, like I said, is to remove the unreacted lithium aluminum hydride. Basically, we have H minus and the H3O plus provided by the acid. They will react to form hydrogen gas and water. Okay, so in fact, adding the acid has two purposes. If you learned this one already, if you have learned this one is to remove the excess unreacted lithium aluminum hydride. The second reason is to convert the alkoxide into alcohol. Right? So there are actually two purposes, and this also unveil the reason why it's so important to avoid having water or moisture from touching the lithium aluminum hydride, because you see this reaction, you will expect to be very fast, right? H minus and H plus, very fast reaction, and most importantly, they generate hydrogen gas, which is highly flammable or even explosive. So that's why we need to avoid the contact of lithium aluminum hydride with water. Okay? So that's the idea. Okay, let's move on to another main dish. Now you see aldehyde and ketone, not much of an issue. Only two reactions. Actually one, because oxidation we kind of learned about that already. There's actually only one new reaction, which is the reduction. But for carboxylic acid, wow. Okay, so there are many more reactions. So there should be like 3 reactions, or even 4. Let me sneak peek. Oh, just 3 reactions. Okay, manageable. So there are 3 reactions. So let's get started. Okay, carboxylic acid, general formula RCOOH. Now remember, one of the oxygen is having double bond with the C. Now, just figure out the remarks. Now, for the general formula, there are 2 types. Okay, before, when we talk about like alcohol, haloalkane, right? So the general formula that we usually use is like this. We have CnH2n plus 1 OH. Well, we have all these like N, right? Something like that. These are the general formula that we commonly use. But you may realize that starting from aldehyde, here, the general formula, instead of using those N and H2N plus blah blah blah, we actually use this representation to show the general formula. Okay, we try to emphasize the functional group rather than looking at the N to N, something like that. So this is how we usually do it. Now, can we show the general formula in terms of CnH2n blah 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 like this? Yes, of course. You still do the same thing, like you try to derive from the general formula of alkane, but like this is what we usually use. Okay, so here we will focus on the functional group rather than the stoichiometry. Okay. Now the functional group here, Pay attention. A lot of students make a mistake here. The functional group of carboxylic acid, a lot of people will say carboxylic group or carboxylic acid group. So the answer is carboxyl group. This is the name of the functional group, carboxyl group. So don't say carboxylic group, okay? Even I may have made mistakes in my notes if I remember, because it feels like more like an adjective, right? Carboxylic group, right? So, but it turns out that it is just carboxyl group. Anyway, now general remarks. All the carboxylic acids are liquid. I mean, the usual number of carbon, if it goes up to like 50, 100 carbon, I suspect that it to be solid. But most of the carboxylic acids are liquid, they're colorless liquid, and they have pungent and irritating smell, which is unpleasant. Usually, we would say carboxylic acids have an unpleasant pungent smell. Okay? So consider as foul smells. Now, think about an example, which is ethanol acid. Now, ethanol acid is the main ingredient in vinegar. Now, vinegar, I'm not sure whether you like it or not. For me, I don't like vinegar. But think about it, if vinegar is not part of our cuisine, then it is quite pungent and having such a bad smell, right? So, in fact, carboxylic acid in chemistry, we will consider as a foul smell. As a matter of fact, a lot of our body foul smell is due to the formation of carboxylic acid, such as like the boys after playing basketball, okay, they have their shirts, underwear all soaked up by the sweat, and that kind of sweaty, smelly, fishy smell is actually coming from the carboxylic acid. Okay, it's actually coming from your, the sebum, right? Basically your skin oil kind of decompose, oxidize into those carboxylic acid. So you get the idea, right? So carboxylic acids are basically having bad smell. Okay, bad smell. Now also, you may realize that carboxylic acids not only have reactions regarding its functional group. I mean, yeah, it does, but after all, carboxylic acid is a weak acid. So you may also expect it to react with a base or react with a metal. Okay, but bear in mind, almost all the carboxylic acids are weak acids. Okay. All right. So physical property, similar to alcohol, because of the carboxyl group, it can form hydrogen bond with its own molecule, and the intermolecular bond, hydrogen bond, is even more extensive than alcohol. So this is the reason why carboxylic acid is having a higher boiling point than alcohol. Of course, we are comparing members of similar number of carbon. Okay, so carboxylic acid higher boiling point than alcohol. Okay. Now let's look at the reaction. So actually, the first reaction is not reduction. The first reaction is acid-base reaction. Okay. This one I did not include here because it's supposed to be a Form 4 topic, right? You need to know, you already learned one carboxylic acid, which is ethanol acid in Form 4. And being an acid, it can always react with base, so it reacts with like metal oxide, metal hydroxide, metal carbonate, metal hydrogen carbonate, right? It also reacts with some reactive metals such as zinc and magnesium, right? So for these, I assume you guys already know, so I would not emphasize in this part, okay? But do bear in mind they do have acid-base reaction, okay? Now, the first reaction is reduction. So, very similarly, if think about it, like carboxylic acid is formed from the oxidation of alcohol, right? So, of course, you can reduce it back to the alcohol, right? So, if you look at this diagram, this is something interesting. Now, first of all, you should be able to tell that ethanoic acid or carboxylic acid must come from a primary alcohol, Because a secondary alcohol, when they undergo oxidation, they form ketone, and ketone is resistant to further oxidation, right? So all carboxylic acid, they must come from a primary alcohol, okay? Now, when we talk about oxidation of primary alcohol, we say that it undergoes two-step oxidation, first to form aldehyde, and then subsequently forms carboxylic acid. So you may expect the reduction do it similarly, right? You may expect to see a two-step reduction. In fact, there is no two-step reduction, okay? So whenever you carry out reduction of carboxylic acid, it will go straight away to form the alcohol, okay? Now, you will use lithium aluminum hydride to reduce the carboxylic acid all the way to alcohol. It happens like this because, like I said, lithium aluminum hydride is a very powerful reducing agent. So it will reduce the acid all the way to the alcohol, okay? Now, you may ask, hey, sir, how about if I use the sodium boron hydride, right? It's a milder, safer, weaker reducing agent. So can we achieve a two-step reduction using sodium boron hydride? As a matter of fact, no. Because, in fact, sodium boron hydride is not powerful enough. So here you can add a remarks here, NaBH4, okay, doesn't work because it is too mild to reduce carboxylic acid, or too weak, okay, too weak. Maybe too weak is better, too weak. It is too weak of a reducing agent to reduce carboxylic acid. So we can only use the powerful lithium aluminum hydride, but when you use that powerful lithium aluminum hydride, it will go all the way to the primary alcohol. Okay, so you see here, boom, boom, okay? So you may ask, hey, sir, what if I really want to reduce the carboxylic acid back to the corresponding aldehyde? What should I do? What you should do is to first undergo a reduction to form the corresponding primary alcohol, and then you carry out a mild oxidation with potassium dichromate to form the aldehyde. So you need to have two steps. And I hope you still remember how can we ensure the alcohol is oxidized to aldehyde but not carboxylic acid. Okay, I hope you still remember. We will use certain experimental setup devices to ensure that the aldehyde will not be further oxidized to carboxylic acid. Okay, so that's the idea. This is the first reaction of carboxylic acid reduction. Now, let's talk about another reaction, which is for the first time, very complicated for the first time you're learning. But later on, it should be quite easy. And this one, please pay extra attention because this one is very frequently asked. Esterification, okay? Very frequently asked. So esterification, judging from the name, it has to do with something called ester, okay? Because this basically means a reaction to make esters, okay? Now, if you still remember, we did talk about esters when we talk about naming. We say that ester is composed of two parts. One is coming from alcohol, another part is coming from carboxylic acid, okay? So, in fact, this is a reaction between alcohol and carboxylic acid. So let me break it down for you. Now this reaction, if you follow the color, it reacts like this. We will say the acid will provide the OH, the alcohol will provide the H. So the OH and the H will combine to form, as you can guess, water. Okay, water over here. Okay, so can you see it? like the OH and the H, if you take it away and you combine them, then you will get water. You will get water. Okay? So now, when they are gone, when the OH is gone, when the H is gone, so what happened is, this particular carbon, it will have only 3 bonds, right? 1, 2, 3. 3 bonds. And this bond is available to join with something else. Similarly, for this oxygen atom, it has only one bond, right? So it has another bond that is available to attach to something else. So what do these two parts do is to connect it to one another. So the red part and the green part, they kind of join together. C bonded to this oxygen atom O. So we have this one. Okay, we form an ester. Okay, you get it? Like this carbon connected to this oxygen, you kind of have this green part kind of like flip over, flip over, like flip to here, and then join with the carbon, then you will have this one. Okay? And this, the entire compound, is called an ester. An ester. Okay? So this is the idea. Now, let's talk a couple of remarks regarding this reaction. So first of all, this bond that is formed right here, we have a name. This bond connecting the acid part and the alcohol part, we call this one the ester bond. Ester bond. Okay? And it is very important to know where is the ester bond, because later on, so first of all, because this ester bond, okay, if you are able to locate it, basically it tells you what the carboxylic acid looks like and what the alcohol looks like, right? This one is coming from the carboxylic acid, this one coming from the alcohol. So that's why you need to know where is the ester bond. This is the first reason. The second reason is later on when we learn about the esters reaction. Actually, the reaction usually cuts at the ester bond. So make sure you know where is the ester bond. Okay? Now the second thing is, when you talk about the naming, when you name this compound, okay? When you name this compound, you see the name has 2 parts, ethyl ethanoate, okay? So the later word here is based on the carboxylic acid. So this part is based on the carboxylic acid. Okay, so if your carboxylic acid has 2 carbons, then we will call this one ethanoate. Ethanoate. Okay. Now for the first word, which is the green part, I hope my green ball pen has ink. This one, okay, will be corresponding to the alcohol part. Okay, the alcohol part. All right. So when you name this compound, you will name the alcohol first, we call it ethyl, and then this part, the acid part, ethanoate. So ethyl ethanoate, okay? So that's why you need to know where the ester bonds are, okay? So you know how many, then you know how many carbons are there in the alcohol and how many carbons are there in the carboxylic acid, okay? Now, another thing I need to say is that you look at this reaction, so it takes place under certain condition and it requires a catalyst. So for this reaction, first of all, you need a catalyst, which is concentrated sulfuric acid. Okay, it needs a catalyst, concentrated sulfuric acid. Without this one, the reaction goes very, very slow and almost not going to react. And also, this reaction, because it's so slow, it needs to increase its rate by heating. So we have to also undergo heat under reflux. Heat under reflux. If you remember, heat under reflux basically allow a long time of heating, but the reactant and product will not escape. So we keep the reactant and product. Okay? And the last thing I want to talk about is, look at the reversible sign. Look at the arrow. Okay. Now, please bear in mind, for esterification, when you are asked to write the chemical equation, you must use a reversible sign because this reaction is reversible, meaning that the ester can actually react with water and go back to alcohol and acid. So bear in mind, when you are writing this equation, you must use the reversible sign. Okay? Otherwise, 1 mark will be deducted. Okay, so that's the idea. Now down here, we have another term. If you study biology, you should be familiar with this term. So esterification here is the name of the reaction. And this particular reaction belongs to the type of reaction called condensation reaction. Condensation reaction. What is the meaning of condensation reaction? Over here. The condensation refers to, okay, formation of large molecule, okay, from 2 or more small molecules, okay, with the removal of small molecules, usually water. Okay, so that means when we have a reaction such that we have small molecules joined together to form a large molecule, and at the same time we will remove some water, then it is considered as condensation reaction. Okay, and this one you can see small molecule joined together to form a large molecule with the removal of water that fulfills the criteria. So that's why this esterification reaction belongs to condensation reaction. Okay? Now, here is a setup. Actually, you've seen that one before. It's a heat under reflux setup. So like I said, this reaction, if we try to actually do it, we need to heat it under reflux for at least 1 hour. Okay? 45 minutes to 1 hour. Okay? So basically, we put everything inside. The alcohol, the carboxylic acid, wrong spelling here. Wrong spelling here. Carboxylic acid. Okay. Concentrated sulfuric acid, which is the catalyst. We add everything inside the flask, and we also add anti-pumping granules, and then we just heat it under reflux. Okay. And we try to use a water bath or oil bath, sand bath, or if you want to use naked flame, make sure you add a wire gauze because the wire gauze can reduce the heat, reduce the temperature of the flame. You don't want to do direct heating because the alcohol is flammable and it's open, so air can get in. Plus the fact that using naked flame, the heating is not as even as the water bath or the oil bath, something like that. Okay, so here, heating and adding the sulfuric acid catalyst can speed up the reaction. And here, this is something interesting. Probably you haven't actually learned that yet. We say that relative large amount of sulfuric acid is used. Okay, now because as a catalyst, catalyst is something that can speed up a reaction, but it will not be consumed. So, in other words, we don't have to add a lot. We just add small amount, and that would be sufficient. Okay, but in this particular reaction, we will add actually a large amount of sulfuric acid. In a sense of catalyst, we will add large amount. The reason why is that here, sulfuric acid is hygroscopic. If you remember hygroscopic, that means it can absorb moisture, absorb water. So they are able to remove the water that is produced. Now, when the water is produced, if you look at this reaction, now this is a reversible reaction, meaning that the reaction is not complete. So it's like if I have 10 ethanol, 10 ethanoic acid, you won't expect to see at the end 10 ester molecules. No, it doesn't work like this. Probably if you have 10, 10, at the end, probably you got like three esters, okay, and 3 waters. This is what reversible reaction means, okay? But this reversible reaction can be adjusted, can be affected if you take away the products. Okay? You see, water is one of the products, right? So if you add a lot of concentrated sulfuric acid, and concentrated sulfuric acid will take away the water, then when the amount of product, which is the water, decreases, more reactant will actually react to form the product to try to sort of replenish the water being taken away by the concentrated sulfuric acid. So by removing the water, more reactant will react to form the two products, which in other words, making more esters. So that will increase the yield of the reaction. So that's why over here we will add relatively large amount of sulfuric acid, okay, because it removes the water produced, shifting the equilibrium position to the product side and increasing the yield of an ester. Okay, so that is the reason why. Okay, a very specific case that probably you need to pay attention to. Okay. Okay, so last reaction for carboxylic acid, which is the amide formation, amide. Now, first of all, do you still remember what is amide? Probably not. Now, let me give you a reminder. Now, this one is a carboxylic acid, right? Okay, and an amide is like this. Okay, this is an amide. Or to be more specific, this is an unsubstituted amide. Unsubstituted amide. Because there is no AQ group attached to the nitrogen atom. Okay? Now, I want you to focus on, okay, these two parts. So, basically, we are trying to replace the hydroxyl group by the amino group. Okay? You can think about it this way. And the amide is characterized by having a CO double bond and CN. Okay, so this is the part where amide is recognized. Okay, the functional group of amide. Okay, so how do we achieve this? There are two methods. Okay, the first one is a two-step reaction. So first of all, we will add PCl3. PCl3 sounds familiar, right? We did talk about that when we talk about haloalkane. Sorry, not haloalkane. Alcohol. Alcohol. There is one reaction called substitution reaction, where we try to convert alcohol into haloalkane. And if you want to convert an alcohol into a chloroalkane, one of the methods is to use PCl3. Right? And immediately it will do the substitution. Now, if we use PCl3 to react with ethanol acid, it will form something looks like this. Basically, a substitution reaction, Cl substitute the OH, forming CO double bond Cl. So this one is what we call ethanoyl chloride, which belongs to the homologous series acyl chloride. Now, the homologous series itself is out of the syllabus, but all you need to know is that this particular functional group is very, very reactive. Very reactive. Okay? So this is quite dangerous. Okay, this one is quite dangerous. And after the first step, we will add ammonia gas. And this ammonia gas will then replace the Cl atom, forming the amide. Okay? So this is the idea, amide and an HCl, okay? So this is how we convert carboxylic acid into amide. First reacts with PCl3 and then reacts with ammonia gas, okay? Now you can also use a thionyl chloride. This is another reagent that can replace the hydroxyl group by the Cl, okay? Now you see, this reaction two-step reaction has some advantage and some disadvantage. The first advantage is that it does not require heating. No heating is required, meaning that the reaction itself is quite fast actually. But the disadvantages is that, like I said, this one is very reactive, and so as PCl3 and SOCl2. All these, including the acyl chloride, they are susceptible to hydrolysis of water, meaning that it will react readily with water. Okay, so especially for acyl chloride, which is this one, it can react with water to give acidic mist. Okay, HCl gas, which is highly irritating. Therefore, this reaction involves hazardous chemicals, which will incur safety issues. So these are the disadvantages. And of course, it requires 2 steps, okay? And more reactor will be needed. So this is the first method. Another method is more straightforward, is to heat it under reflux with ammonia solution. Heat under reflux with ammonia solution. So you see here, we add ammonia solution and then we heat under reflux, and sooner or later, the OH will be replaced by the amine group. Then it forms an amine. Okay. Here, pay attention, is that you must heat it under reflux. You must heat it under reflux, because if you not heat it under reflux, okay, if you not heat it, then you realize that this is an acid, this is a base. They will actually undergo what? They will undergo neutralization reaction, right? They will actually form a salt. Okay, so you don't want a salt, right? You want the amine. So you must heat it under reflux. Actually, under heating, it will drive this salt into the corresponding amine. Okay, therefore heating must be required. Okay, so 2 methods, both of them you need to know. So that would be the reaction for carboxylic acid. Okay, now let's look at those practice questions. Okay, again, pause the video, try to figure out yourself, and then we check the answers. Here again, only the organic products. Don't give me any inorganic products. Okay, so let's check. This one is an aldehyde, right? And this is an oxidizing agent. So aldehyde can be oxidized to carboxylic acid. So we have this one, okay? Propanoic acid, okay? Then this one, oh, we have a ketone. Now you should be able to tell this one is a ketone because there are 2 AQ groups here, right? And this one is a secondary alcohol, right? Again, 2 AQ groups here. Okay, so we have an oxidizing agent. So the question is, okay, which one will undergo oxidation? Now the secondary alcohol, of course, it will undergo oxidation to form ketone, but can ketone undergo further oxidation to form carboxylic acid? I don't think so. So it turns out that there is only one reaction going on with the hydroxyl group here. Therefore, the product would be like this, okay, with like a diketone. Okay? And here we have a benzoic acid, and we use lithium aluminum hydride. Okay? Now, also try to look at how I put down the conditions and reagents. You see 1, 2, because if you remember the reduction of carboxylic acid or the reduction using lithium aluminum hydride, you need to do 2 steps. First, reduction, and then add acid to remove any excess lithium aluminum hydride. So this one, remember, this is a very powerful reducing agent, so it will reduce it all the way to the alcohol. So you should draw the structure of this corresponding alcohol, okay? Like this, okay? And then, here, D. Lithium aluminum hydride again. Here we have a carboxylic acid and a ketone. So, of course, no matter it's ketone or carboxylic acid, they will all be reduced back to this alcohol. So this one should give you this one, okay? So goes back to the alcohol and alcohol, just like that. All right, so here, so over here we have again two functional group. We have aldehyde and we have carboxylic acid. So we use NaBH4. So remember, this one is a weaker reducing agent. It can only reduce aldehyde but not carboxylic acid. So we should see this one, okay? We should only see the aldehyde being reduced to alcohol, but not the ethanoic acid, okay? Now this one, we have propanoic acid, and then we have alcohol, concentrated acid, heat, that is hinting towards, esterification. So here, let me show you. Now, this part will be the acid part, and like I said, the acid will provide the OH, the alcohol will provide the H, right? And then this part will be the alcohol, okay? Then what we do is we try to put down, okay, the acid first. It doesn't matter, but this is usually what I did. Acid CH3, CH2, C double bond O, right? Okay. This one is this one, and then the green part here, the alcohol with the oxygen attached to the carbonyl carbon. Okay, I will put it this way: CH2, CH3. Okay, so that would be the corresponding ester. Okay, remember, the acid part, it sacrifices the OH, and the rest of them, you just draw it like this. And then the alcohol, it will sacrifice the hydrogen atom because these two parts will combine to form a water. And the rest of them, you have the oxygen atom connected to this carbon because, like I said, this one you will do a swap, you flip it around and then join it here. Okay, so that's the idea. And then lastly, this one we have. This one is okay, an acid, a carboxylic acid is phenyl ethanoic acid. So first by PCl3 followed by NH3. So this one is to form an amine. This is to form an amine. So CH2, C, double bond O, NH2. Okay? So this is the idea. Okay? Oh, we have more practice question. Did you guys already do it? If you have done it, then you can continue. If you haven't, pause the video and then we will check it later. Okay, so here we have carboxylic acid and then we have ammonia, but this time there is no heating. So this one could be tricky. This is not a reaction that we have learned in organic chemistry. This is actually a neutralization reaction. So the product, okay, it's actually a salt. Okay, because it is just a neutralization reaction, so it forms a salt. Okay, this one is also a very tricky question because but this is commonly asked in the DS exam. Now you see we have one organic reactant and we have concentrated acid heat. When you see concentrated acid and heat, we will be thinking about two things. One is dehydration of alcohol, right? Dehydration of alcohol. You remember, for alcohol, it can undergo dehydration to form alkene, right? So this is one way of thinking. Another way of thinking is it may undergo esterification, okay? Because esterification also we need to use concentrated acid as the catalyst. So here, actually, we have only one reactant, and we don't have alcohol here, right? So could it be just a dehydration? Now it turns out that if you look at this particular compound, it has two functional groups. It has a carboxylic acid group, carboxyl group, and then it has an alcohol, the hydroxyl group. So in fact, this molecule is quite long, right? 5 carbons, right? So in fact, we can have this hydroxyl group reacts with this carboxyl group to achieve the esterification. Okay? Now here, I'm trying to show you what is going on is, okay? Again, the acid is going to sacrifice the OH, the alcohol is going to sacrifice the H, so take away the OH, take away the H. So basically, the oxygen atom is going to connect it to this carbon, right? Let me give them some numbers, right? 1, 2, 3, 4, 5, and oxygen atom, right? Okay, so let me use a triangle. Okay, so altogether, you will expect to see these 6 atoms will form a ring, because now it is the head reacts with the tail, or the tail reacts with the head, right? It doesn't matter. So it will form a ring with 6 members. So it is going to be a hexagon. Okay, so let me show you. So we can have the ring like this. Now, but bear in mind, one of them should be oxygen atom, okay? And then we will have the double bond O here, and that would be the answer. Don't worry, let me show you how do we match one another. So we can have the first carbon here. So this is the first carbon, okay? And then here, second carbon, third carbon, the fourth carbon, and the fifth carbon, and the oxygen atom, okay? So once they undergo esterification, so these two join together, and therefore, this is what we expect to see, okay? So it forms a cyclic ester, okay? All right? Now, J here actually has a similar concept. Again, you see one compound and then you just heat it, you don't have any other reagent. It's fine because you see this compound has 2 functional groups. It is an amine, this is a carboxylic acid. Now actually amine behaves quite similarly as ammonia. So in fact, the head and the tail can react. So it will form an amine. So here again, the carboxyl group will provide the OH, will sacrifice the OH, and here the nitrogen will sacrifice one of the H, because you only need an extra H to form a water, right? And then it is the nitrogen that is connected to the carbon, right? Because remember, for amine, you need to recognize that it is the C connected to the N, right? C double bond O bonded with the N, right? So here, again, I make use of this number. 1, 2, 3, 4, triangle. So now we have 5 atoms forming a ring, head to tail. So 5 members should give you a pentagon, right? So it's going to be like this: 1, 2, 3, 4. Okay. Now, but remember, one of them needs to be a nitrogen. Okay. Just like the ester, one of them is the nitrogen, and we can have this one. Okay, that is the answer. Okay, try to kind of separate them. Okay, again we trace back those numbers. So here, 1, 2, 3, 4, and the triangle is over here. Okay, here, okay, here, Okay, so it will form a cyclic amide. Okay, a cyclic amide. All right. All right. So the last one here. So we have this compound, and then you see it has constant sulfuric acid again, heat, and also the methanol. So what products do we expect to see? So you see all these, combos, right? It obviously hints towards esterification. So you have again carboxylic acid providing OH, the alcohol providing the H. These three atoms form of water, and then the oxygen joined to the carbon here. So you may expect to see C, 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 double bond O, and then O, C, right? You should expect to see something like this, okay? Forming an ester. Now, but sometimes you need to pay attention, okay? You see this compound has more than just one functional group. It has the OH as well. And like I said, the OH, when you have constant sulfuric acid and heat, it will undergo dehydration. So very likely that it will form a double bond here. It cannot form a double bond here, otherwise it has 5 bonds, right? So in fact, the product will be like this. Okay? So it will form an ester with an alkene. Okay, an ester with an alkene. All right? So that's the idea. Okay, let's quickly do question 2 as well. Here we have 2 organic compounds, and explain why the 2 compounds have. Where's my blue ball pen? Over here. And explain why the 2 compounds have similar boiling point. Now again, usually we will say why 2 compounds have different boiling point, but this question is asking why do they have similar boiling points. But anyway, it all boils down to the intermolecular force, so maybe we start with looking at the functional group. So both have, okay, carbonyl group, and both are polar, okay, and they have similar molecular size and shape. So their intermolecular van der Waals force, okay, are similar. So we basically make use of the 3 factors affecting the strength of van der Waals force, and we just lay it out, right? They have the same polarity, similar. They have. I should put it this way: both of them are polar, but cannot form hydrogen bond. They have similar molecular size and similar shape. Both of them are linear. So when all the 3 factors are similar, obviously the intermolecular van der Waals force are similar, and accounting for the similar boiling point. Okay. Now distinguish the 2 compounds with a chemical test. Now this one is a ketone. This one is an aldehyde. So to distinguish between the 2, we can make use of acidified potassium permanganate solution, right? So only B changes from orange to green. Okay? That's the idea. Now, you may ask, hey, sir, can I say that, can I do like a reduction, okay? Reduction, but both can be reduced, right? Not a good idea. Yeah, so I think this is the best. This is the best chemical test. Anyway, okay, let's move on to another question here. So this one is a very simple chemical experiment. We have Test tube containing a mixture of ethanol, propanoic acid, and corn sulfuric acid, put into beaker of hot water. After 10 minutes, the content in the test tube was poured into the cold water, and upon settling, we see 2 layers of liquids. Okay, so we put all the reactants and the catalyst, put into this test tube, heat it with a hot water bath. Okay, pour it into cold water. 2 layers of liquid, and this, a thin layer of immiscible liquid, has a fruity smell. Okay, has a fruity smell. So when we see fruity smell and it is immiscible with water, it is hint towards ester. Ester. Okay, we haven't talked about the property of ester yet. Okay, it will be our next video. But ester has a distinctively fruity smell. So basically, in chemistry, when you say there's a liquid that has a fruity smell, very likely to be an ester. Okay? Now, part A. Draw the structure of the compound responsible for the thin layer of immiscible liquid, the one with the fruity smell. Okay? Here. The one with the fruity smell. Draw the structure and state the name. Okay? Now, this is an ester form between ethanol and propanoic acid, right? So the propanoic acid is here, CH3, CH2, COO, and then the alcohol part would be coming from the ethanol, right? So just like this. So the name, we will start by naming the alcohol first. So it is an ethyl propanoate. Okay, ethyl propanoate. Okay, and then write the chemical equation for the reaction taking place in this experiment. So chemical equations, we have the ethanol, right? CH3, CH2, OH, reacts with the carboxylic acid, which is propanoic acid. Okay, and reversible sign because it's an esterification, forming CH3, CH2COO, CH2CH3. This is the corresponding ester, and don't forget we have water. Okay, now this is the way how we show the condensed structural formula of an ester, COO. Okay, and do bear in mind this part. Okay, is the acid, and then this part is the alcohol. Okay, so make sure you know how to interpret these different representations. Okay. Now for this experiment, the yield of the ester is very, very low. So draw a labeled diagram of an experimental setup that can be used to perform the same reaction with much higher yield. So for an esterification reaction, we need to do heat under reflux. So we need a heat under reflux setup, which is quite easy. So you will draw a flask here, okay, which contains mixture of reactants and corn sulfuric acid. You will show anti-pumping granules. You will heat it, and over here you have the reflux condenser. Okay, and the water in here, water out here. Okay, so that would be the diagram. Okay. Right. Okay, so down here, no matter how long the reaction was taking place using the setup in part C1, the yield never reaches 100%. So just a reason accounting for this. So the reason is because if you look at this equation, it is reversible, right? That means the product is able to react to form the reactant. So you can never have 100%. You may have 99.999%, but they can always go back to the reactant. So this is the characteristic of reversible reaction. So here, what we're trying to say is simply because the esterification reaction is reversible. Okay? Because the esterification reaction is reversible. Okay? So that's that. Alright? So we will stop here today, and next lesson we will talk about the reaction with esters and amine. Okay? So see you guys later. Bye bye.